Okay, in this video, I would like to talk about stress transformation, mainly mechanical stress, could be stress tensor, could be strain tensor, or for the other quantities like moment of inertia and similar quantities that can be expressed in a form of tensor, mostly symmetric tensors. Uh, we would focus on using index notation that simplifies and makes the calculation more in line and consistent, and using Einstein summation convention. I will discuss the stress rotation for 3D and 2D plane stress, and then we focus on plane stress to 2D transform the stress equations. So as a result of rotation of a stress field, and then we will get into some foundation equation for Mohr circle, and we take it from there. The plan is to put this foundation in this video, and then in the next video uh, uh, discuss how to construct Mohr circle and how to extract information from it, which is a very usual visual or graphical method, and also expand on 3D stress rotation and how to calculate when you have a three-dimensional. Mohr circle is possible to go 3D. It has some special case, but I personally prefer to use the analytical approach for a 3D case. Okay, so let's start with the index notation. If you have seen my other videos on Beam, I have discussed this index notation, but I would give it a quick review and a refresher here. So if you have a quantity like a vector, let's say A, for example, we give it a subscript index I, and in 3D, this I becomes basically the representation of the vector components A1, A2, A3 in a Cartesian coordinates, shall we say, or in any coordinates, three-dimensional. Now, if you come and have this as a two free indices, so we call it tensor. Technically speaking, any quantity is a tensor, but the order is different. This is the tensor of first order. This is tensor of second order, number of free indices. And then here, usually we represent this by a 3 by 3 matrix, and so on. So that is a given. Now, Einstein summation convention tells us that if you have an expression, let's say A, I use A here for representative symbol here. Let's say if you have I, for example, times inner product of two vectors bi, Einstein summation convention says that if you have a repeated index, you should sum up on that index. And this is basically an inner product of two vector. Or for example, if you have a tensor second rank matrix multiplied, say, by bi, here we, let's say, call it bj to be more straightforward, doesn't matter, as long as I have one free index here and two dummy indices that they repeat, I have to sum up on that one. So I takes 1, and then the j goes 1 to 3, and then r goes to 2, 2, 1, b1, and etc. So these two simple rules can help us a lot in writing the expressions and condensing them and so on. Okay, so having said that, we move to the concept of rotation. In many occasions or on many calculation, we need to calculate the components of a vector, or in general a tensor. Here, when I say tensor, I mean mechanical stresses that we may have in a domain, in a body, for different orientations. So if I have, for example, a body here, and for example, I get my coordinates established, then any point that has a tensor, let's call this tensor S I J, at this point, at any mathematical point or material point, we can have an acting tensor. Uh, it has components, as I mentioned, 9 components, as I said here, and then vector, which is the component of this tensor on a defined surface, has 3 components. These components will change if I come here and change my coordinate system. Let's say I rotate x, y about z axis, and I get x prime, y prime. Obviously, the component of these tensors and vectors would be different. I will discuss why you need to know how to do this from a mechanical engineering or strength of material point of view, but this is what we have. Now, what is the Rij? Rij is a 3 by 3 matrix, if you write it in matrix format, but I write it in index notation, and that is what we have here as Ni Nj plus delta Ij minus Ni Nj cosine theta plus Eij k Nk sine theta. Let me explain what I mean by each one. Now here, for example, if I come here and rotate my xy about z axis, therefore I am rotating about a vector or along the axis of rotation. If I rotate it by right hand rule, well, this is actually in the picture that I have here, I have rotated using right hand rule about the minus z direction. So my unit vector would be -1. You could rotate xz plane about y or any orientation. So that axis that you are rotating your coordinates should be represented by a unit vector, and that is n. So that n is our unit vector. Now, theta is the angle of rotation. For example, here, this is my theta. Sorry, this is my theta, which is equal to this one. So let's say 45, 10, 20, 90, whatever is the angle is there. Now, what is EIJ? EIJ is called permutation symbol. And the definition goes as follows. So if you have indices of EIJ, let me write it EIJK, and it is in order like 1, 2, 3. In this order, clockwise, shall we say, then epsilon 1, 2, 3 is 1. Similarly, is epsilon 2, 3, 1. They should be in order. And similarly, epsilon 3, 1, 2. But if you go the opposite direction, like say 1, 3, 2 is minus 1. Similarly, 3, 2, 1, and similarly 2, 1, 3. So these are the values. So if you go in one direction, it is defined as 1, otherwise it is minus 1. If any index is repeated, then epsilon ijk is 0. So for example, epsilon 1, 1, 2 is 0. Epsilon 1, 2, 2 is 0, etc. If any index repeats itself, then it is 0. Otherwise, it is, as I explained, 1 or minus. And sine theta and cosine theta obvious. And this is Kronecker delta. Which has also a definition. It's equal to 1 if I equal to j, is equal to 0 if they are not equal. For example, delta 1, 1 is 1 equal to delta 2, 2 equal to delta 3, 3. But delta 1, 2 equal to delta 1, 3 equal to delta 2, 3 equal to 0. So these are the definition. You may feel that we are having we are introducing too many maybe definition and symbols here, but trust me, this will help a lot, especially in 3D. Now, having that, we come back here and say, okay, if I have a tensor, let's call it stress tensor. I call it Sij. You may call it sigma ij. Sometimes we use Greek notation or Greek letters, doesn't matter. This is a stress tensor. So it has 9 components, and we represent that by this. Now, how do I transform this? Basically, I would like to transform this, find the components in a rotated coordinate system. Let me do this with a vector, and then we go and do it with a tensor. For a vector, let's say call force vector. Fi. This is a force acting. How do you transform a force vector or velocity vector or any vector that you want to transform? By transformation, I mean that you have xy and z. And let's say you have a vector here, f. This is your vector. Let me maybe try it in different colors so it doesn't mix up with the coordinates. This is my vector. And then I come here and rotate my coordinates x prime, y prime about z. Now, if I do that, then therefore after rotation, let's call it f prime, shall we say, f prime I is r I j f j. So this is my original vector in x, y, z coordinates. This is my rotated or transformed vector, or if you like, components in x prime, y prime, z prime coordinates, the rotated. This is all we are after. Okay, so and then r is given by this. Let me give you a quick example here. Let me give you a quick example here, and that is, let's say, example. Let's consider it a 2D, x and y, and purposefully I consider my vector here like this. Let's say our f is along the y-axis. Obviously, my fi would be 0, and let's assume this has a unit magnitude. So my fi would be 0 and 1. Now, if I come and rotate my coordinates by 90 degrees, so therefore my y prime comes here and my x prime goes there. So I rotate xy about 90 degrees, right hand rule. So what would be my n? My n would be 0, 0, 1, because I am rotating about the z axis and right hand rule. So therefore my unit, I'm rotating about this axis. So I come here and say, okay, f prime, if you like, would be what? Would be my r. I take it to the, and I use this for the purpose of calculation my r. And if you do that, then it would be cosine theta. Let's say my theta here is 90 degree. Cosine theta, and then sine theta minus sine theta cosine theta. And this should be multiplied by my fi. So this gives me what? This gives me 1, because this is 0. This is, let's say, sine 90 is 1, so 1. And then this is minus, and then this is cosine 90 is 0. So this is my my coordinates, my components of my vector which is sitting here but in the x prime y prime coordinates. And this is obvious that, because this is sitting here, so my x prime here, so this will be 1, and there is no component in the y prime direction. This is a very quick example using these things, and this is basically Rij for this unit vector, and theta is 90 degrees. One term here, maybe I expand here, and that is 1 2 or 1 3, shall we say. If you come here and say, okay, I want the 1 2, and then 3 is nk is 1, so this becomes 1, the whole thing, and then sine theta is remains here, which is actually 1. Okay, so for a tensor, we just follow the same thing. For rotation, when we have stress tensor, we use, let's say, S prime by J is R by K, R J L S K L. This is a quite compact expression here using Einstein summation convection. So if you want one component, I will expand few terms here, not fully, and then I becomes 1, J becomes 1, but you have to sum up on K because K is repeated, and also F. And this gives you the components of your stress, which is initially defined in your unrotated initial coordinates, let's say here, or any coordinates, and then after rotation you will get the components of that stress in the rotated coordinates. Let's say take the two-dimensional, for example, and then if I come here and say, okay, let's expand this for S prime 1 1. So here this is I, this is J, these are free indices. So I will be 1K, J will be 1L, SKL. Now you have to expand. Let's expand on K first. So RK, K becomes 1 2 3 1, and then I expand, and then I keep L, and then expand on K will be 1 L. So this is one of the term. 1 K is 1, then K becomes 2. Actually, I could factor out maybe I do it here, and then expand on K between these two, and then this becomes 1 2 S 2L, and then becomes R1 L, R1 3 S 3L. And then you come here and then expand on L, and similarly here. And then for each term you will get a product of several and R comes from the rotation matrix, as I mentioned here. This is RR. And then you substitute, and then you get S11. Similarly, you could get S prime 1 2, S prime 2 1 is, let's say, assume symmetry, and then S prime 2 3. You may say, okay, I want to do it 3D. That's fine. You could go S12, S prime 1, 3, S prime 2, 3, and S prime 3, 3. So you will have a matrix of this transform which has S prime 1, 1, S prime 1, 2, S prime 1, 3, symmetry. When I put this symmetry, S prime 2, 2, S prime 2, 3, again symmetry, again symmetry, and then S prime 3, 3. And each one can be calculated using this transformation. If you want to go geometric way, it is a mess. It is very, you know, takes time. It is susceptible to making error and so on. And if you want to go, you can also do this in matrix multiplication. But again, in matrix multiplication, you have to be careful about the order when you multiply two matrices with a vector and so on. Okay, so this is the best way, I believe, to do stress transformation. On the side, you can note here that even if you have a third order or third rank tensor, let's say ijk, which has 27 components, you just expand on this, and you are good to go. Of course, it has some algebra and some summation to work out, but that is not a big deal. Okay, let's establish some vision or objectives here. Let's assume that you have let's say a bar, and then this is under some load. And then at a material point, you develop some stress. If we zoom in to that point and then consider a stress element, as we call it, and we define a local coordinates like x, y, the stresses at that point are defined like this, at least in 2D, two-dimensional plane stress. So these are Sx and Sy are normal stresses, and tau xy, which should be equal here because of the equilibrium, is shear stress. Now, when we have tension for normal stresses based on this coordinate system, is positive, because if you apply a stress on a surface which it has its normal in the direction of your defined coordinates, and the stress is in that direction, it is positive. So this is positive. This is also positive because you have this surface here, its normal is in the negative direction, and then your stress is also in the negative direction, so negative times negative becomes positive. Similarly for Sy. Now, for tau xy is the same. So on this plane, this is my normal is in the x direction. So therefore, my positive tau xy should be in the y direction. So these are the definition that we have for stress signs. Now, if I start to stretch this bar, there is no guarantee that it will crack or failure will happen perpendicular to the direction of my force applied. It could happen in different direction. And sometimes we would like to find this direction, and there is a reason why it happens. That depends on the material property, if the material is ductile or brittle. That discussion, I'm not getting into that right now. But in general, material could fail in different direction that the applied force. And that is the foundation that we would like to see at what orientation based on some given initial condition, at what orientation our stresses becomes maximum. By maximum, say that if I come here and divide this f by a roughly, let's say you have a here, which is your cross section A. So this is your average stress at any cross section that you consider. But because of this phenomena that we have, there might be some orientation that gives you a bigger stress, and could be shear, could be normal, um, depends on the initial condition or initial state of the stress. And therefore, we would like to see if I come here and rotate this element, roughly sketch here as if I rotate this element to have x prime, y prime, which is obviously rotated with reference to initial xy by theta, then what would be my stresses? Could even change the, and what would be my shear stresses, top, right, etc. And how much should I rotate to get those maximums? So these are the questions that I will get back to it, but just wanted to give you a quick heads up here what we are getting to. Okay, having said that, a brief explanation about why we care about finding components of a vector or a stress component in rotated coordinates versus the initial state of the stress. We'd like to do it in 2D and then obviously later maybe in second video in 3D based on the explanation that I gave you here. So in this 2D, let's consider this stress state to be the initial state, and then we take it from here. Now, what I would like to do is obviously here my coordinates, which is x prime, y prime, here is, this is my initial one, x and y, and the x prime, y prime is the coordinates which is rotated. So the first thing that you should do, you should define your n, and this is 0, 0, 1, because this is right hand rule and z is perpendicular to the screen. So I'm rotating about that axis, z axis, with this unit vector. So this is my theta. I keep theta as theta in general, could be any angle. And then I use my explanation that I gave you here. I use this formula to find the components of my rotated one. Obviously here my I go from 1 to 2, j go 1 to 2 because it is 2D, and then k and n also go from 1 to 2. So I will not have any term which has a third order. So if you do that, then for example, for S prime 1, 1, you will get R11 square S11 plus 2 R11 R12 21 and R12 square T, sorry, I should say S. Let me change these things to S So we are consistent. S2, 2. So on the side, let's say that S is a matrix of symmetry and S2, 2. And I want S prime, which is S prime 1, 1, S prime 1, 2, symmetry, and S prime 2, 2. So this is the S prime 1, 1 of the rotation in the X prime, Y prime coordinates. And my R, or Ij, would be, for this case, would be cosine theta sine theta. We had it before, minus sine theta cosine theta. So look what I get for S prime 1, 1. R11 is, so this becomes cosine theta square S11. Then this term R11, which is cosine theta, R12 is sine theta. So this becomes 2 sine theta cosine theta. And this is R21. R12 and 21 are identical, so I write it as R12 because this is equal to R21. Sorry, I meant actually I meant the S, not R. S21 is equal to S12. And similarly here, I rushed into this one. So this becomes, okay, so that is good. Sorry about that. So this becomes S12. And the last term, because 1, 2 is sine, so this becomes sine theta square S22. This is my first equation. The second one, which is S prime 1, 2, and a third one, which is S prime 2, 2, these two terms can be found similarly by expanding on I. This here basically is I equal to 1, j equal to 2, and here is I equal to 2, j equal to 2 as well. So if you do that, I'm not going to do that here, you will get a set of equations that I write it here. S prime, let's call it 1, is cosine theta square S1, 1 plus 2 sine theta cosine theta S1, 2, and plus sine theta square S2, 2. And S prime 1, 2, which is the shear stress, becomes minus S11 minus S22 divided by 2. Maybe I don't write it right now in terms of, later I will write these things in terms of later I will write these things in terms of 2 theta, but let's keep it as is. So I wanted to jump one step, but maybe it's better not to. So let's write it as prime S prime 1, 2 is actually equal to minus S11 sine theta cosine theta plus S22 sine theta cosine theta plus S12 times cosine theta square minus sine theta square. And finally, S prime 22 becomes S1 sine theta square plus S2 cosine theta square minus 2S12 sine theta cosine theta. So these once you have theta, simply you can calculate each component of this rotated or stress tensor in the rotated coordinates. This is for this case. Simply here you can see that if you have a three-dimensional, therefore our rotation matrix will become three-dimensional and our components will be 3 by 3. So easily you can do the same for them. You will have two more elements to calculate. At the bottom line is this. Now, let's see what we have covered, what is left to cover in this video. I have talked about the first one, index notation and stress summation. Stress rotation, I discuss it, how to rotate a stress. This formula is very important. And also a 2D that we are working on. These are the 2D transformation and foundation for Mohr circle. I will not get into the Mohr circle, but I will initiate the discussion. Now, Mohr, which was an engineer, looked at these equations. And when you look at these equations and pay attention to this, you see that you have a lot of cosine theta square, 2 sine theta, cosine theta, sine theta square. And from trigonometry, we know that these things can be written in terms of 2 theta. For example, in trigonometry, we have 2 sine theta cosine theta is equal to sine 2 theta. Cosine theta square is 1 plus cosine 2 theta divided by 2. And similarly, sine theta square is 1 minus cosine 2 theta divided by 2. So simply what he did, he replaced this cosine sine theta, everything which is in terms of theta, in terms of 2 theta. It is a lot of algebra here. I will not go through it. But once you do that, and then come here and then form the expression of sine prime 1 1 square plus sine prime 1 2 square. Form this expression after you replace theta by 2 theta. And of course, you can find for the third one. And if you do that, then you will get an equation or a set of equations that looks like this. That now here I would like to simplify this a little bit here and write when we have similar indices, I will write 1 and then I will replace my 1 and 2 because here x is 1 and y is 2 in the notation that we have, because we use index notation. But I will replace or write s prime 1 1 as s prime 1, s prime 2 2 as s prime 2, s prime 1 2 as s prime, sorry, maybe I should say x and y to be more consistent than xy. Okay, and similarly for s, and s11 is sx, s22 is sy, and s12 is equal to sxy. Sometimes we write this as tau to indicate that these are shear. Symbol doesn't matter much, but sometimes it is useful to use the traditional symbols so we can compare with other references or sources. If you do that, then you will get a set of equation that I write it here, which is s prime x is sx plus sy divided by 2 plus sx minus sy divided by 2 cosine 2 theta plus sxy sine 2 theta. And similarly, s prime xy is minus sx minus sy divided by 2 sine 2 theta plus sxy cosine 2 theta, and then s prime y is equal to, similar to this one with the change of sign, sy divided by 2 cosine 2 theta minus sxy sine 2 theta. So these are the result of writing the theta in our transformed equation. These are transformed equation, original transform, and then if you write theta in terms of, or the trigonometric expression in terms of, or functions in terms of 2 theta, you will get this. Now then you come here and then form this expression that I mentioned using this expression, and then you will see that the result is equation of a circle. That is why Mohr circle is born, or discovered, shall we say. And then we will discuss this later, and but this is the mathematical foundation that I wanted to establish, and then later we can basically mention this formation, and then we can look at the equation of the circle in terms of the S or normal stresses and shear stress coordinates. Okay, I guess that's good enough for this video. It took a little bit longer than I expected, but it is always like this. I hope this establishes the foundation for going to the second video and maybe third video. If it takes longer, I make it 3 videos. And in the second video, I will focus on Mohr circle for 2D stress transformation or plane stresses. And in the follow up to that, maybe the same video, maybe another one, I will look at the 3D stress treatment in terms of the three-dimensional. As I mentioned, Mohr circle is capable of doing the 3D, but it is not a preferred method. Mohr circle is very useful in visualization of this stress transformation and understanding. It's quick and it is visual, it's graphical. But when it goes to 3D, it is okay, but not very, it loses its merits. So I would prefer 3D analytical approach for 3D rather than Mohr circle. Okay, thank you.